Let's talk just about ideal transformers. The ideal transformer, it is a two-port device. It has an input port. We call that the primary, the one that is facing the generator, the one that receives power. And we have a secondary port on the far side, which is the one that delivers power to the load. We define two voltages, V1 and V2, the primary voltage and the secondary voltage, and we also define two currents in the primary I1 and in the secondary I1 with those directions. We define a parameter that tells us what transformer we're talking about, A to 1, as shown in there. A, by industrial convention, is greater or equal than 1. And the behavior of the transformer is given not by 1 but by two equations. V1 is A times V2, and at the same time, I2 is A times I1. This is what we call a step-down transformer because it receives power at a higher voltage and delivers the power to the load at a lower voltage. In this transformer, the primary is also called the high voltage side and the secondary is called the low voltage side. Now we talk about the step-up transformer. It is the very same one that we had before, but the mirror of it. We have flipped it about so that now the low voltage side faces the generator and the high voltage side faces the load. A continues to be greater or equal than 1. That is by convention. But look at the way we introduce that in the diagram. Now A is on the secondary, V2 is bigger than V1. The behavior tells us with equations that speak louder than words. V2 is A times V1 and I1 is A times I2. Now the high current side is on the primary and the high voltage side is on the secondary. We call that a step-up transformer. I repeat, the primary now is the low voltage side and the secondary now is the high voltage side. In the power system, we use both step-up and step-down transformers. Check this out. We have a generator that is delivering power at about 20, 25, 30,000 volts. It sounds like a lot, but it's not high enough to transmit power. What do? We use a step-up transformer to raise the voltage to about 500,000 volts here in the province. And once we arrive near town, then we use a step-down transformer to lower the voltage to 100,000 volts perhaps, distribute that to different parts of town, to Richmond, to Vancouver, to Burnaby, and then there we step down further to, let's say, 25,000, and then we go to different neighborhoods, and there we go down to 12,000, 10, 5,000, whatever, and eventually to transformers that step down to 120, etc. volts. That is a chain of step-ups and step-down transformers in a power system. Much more about this will be said next year in AC 373, so stay tuned. But what about power? After all, we are electrical engineers and our interest in electric power is enormous. What about power? Well, power in the primary is going to be the input power. It's going to be V1I1, absolutely. And the output power, the power in the secondary is going to be, of course, V2I2. But because of the behavior of the transformer, we know that V2 is V1 over A, and we know that I2 is A times I1. When we cancel out A's, we get that the input power and the output power are the same. This is a marvelous machine. But remember, this is a wish, an engineer's a wish, an ideal device. That's why it consumes no power, because it's ideal. The real machine is very good, but not this good. It's ideal, eh? Now, the transformer works also for a third purpose. It transforms voltages, we saw that. It transforms currents as well, but it transforms impedances. Let me see what I mean by that. Let's connect to the secondary and impedance Z2. That impedance, of course, is V2 over I2, Ohm's law, right? No surprise there, Ohm's law. Z2 is V2 over I2. But on the primary side of the transformer, all that the primary system sees are the voltage, V1, and the current I1. So on the primary, the apparent impedance is Z1, which is V1 over I1. But V1 is A times V2, and I1 is I2 over A. So that means that the impedance that the primary system sees is A squared times the actual impedance connected to the secondary of the transformer. The transformer can be used to transform impedances as well. Going from low voltage side to the high voltage side, we multiply the impedance by A square. Of course, we could use it backwards and connect the Z2 on the higher voltage side, and in that case, then the impedance on the far side is going to be Z2 divided by A square, your choice. Going up, going to higher voltages, we multiply by A square. Going to a lower voltage side, divide by A square. What do we use that for? Remember matching impedances last term? Remember that if we had, let's say that is an amplifier, and we have represented that using a Thevenin equivalent, and we know that the Thevenin resistance is 800 ohms, and we want to connect to the amplifier a speaker, and the speaker has an impedance of 8 ohms. You remember the maximum power transfer criterion from first term, and we know that that speaker will not absorb maximum power from the amplifier, so the sound in the speaker is not going to be great. For that speaker to absorb maximum power, it should present an impedance of 800 ohms to the amplifier. How are we going to do that? Well, we put between the speaker and amplifier an ideal transformer. What should be A? What should be A so that this 8 ohm resistor, that is a representation of the speaker, looks like an 800 ohms impedance in the eyes of the amplifier. A has to be 10, so that 10 squared times 8 is 800 ohms. That's how we use transformers to match impedances for maximum power transfer. Let's summarize what we have seen so far. We need transformers. Ideal transformers from the low side to the high side multiply voltages by A. Divide currents by A. Multiply impedances by A squared. Power passes through the transformer unaffected, P, Q, and S. The transformer is completely transparent to power. Now let's go into a tutorial time of the ideal transformer. Consider this exercise. This is a circuit, a power system with a generator on the left, and this one represented by a Thevenin equivalent, a load on the far right, represented by two resistors and this inductive reactor, and a transmission system represented by this inductive reactor here and there, and the capacitance and those two resistors. There are two transformers there, a step-up transformer on the left and a step-down transformer on the right. The voltage source has this value. And the impedances are given for all the elements in the system, as well as the transformation ratio for the step-up transformer 2 and the transformation ratio for the step-down transformer 3. Now, we are asked to find VRMS, IRMS, apparent power, active power, and reactive power at the source. We say, fine, there is an easy way to do that. How about if we refer the impedances from one side to the other in the step-down transformer? Let's do that. The first thing I'm going to do is represent the voltage source with a phasor, an IEEE phasor, an RMS phasor, 100 volts with 35 degrees. And then we say we can refer the impedances on the far right to the high side of this step-down transformer. How? Multiply 111 by 3 squared. Those 3 are multiplied by A squared by 3 squared, and we have 9, 9, and J9 ohms. We have referred those 3 impedances to the high voltage side of this transformer. And then what? And then we take all of those, and I'm going to refer them downhill to the low voltage side of this other transformer, so that we have a circuit in the vicinity, in the area of the generator, and we can solve for VI and power in that generator. How? I'm going to divide all of those impedances by 2 squared by 4, because I'm going downhill. I'm going to the low voltage side of the transformer. Easy. This one is 2, but all the others are going to be divided by 2 squared by 4. This is going to be J2. This is going to be 1, in negative J1, etc. All of them have been divided by 2 squared. And once we have this one, we use just the normal method of solution to find what is the current in the source. probably what I would do is find the equivalent impedance, combining all of those impedances, divide this voltage by that equivalent impedance with that current, conjugate times this voltage. That would be the complex power, and there I would have P, the active power, Q, the reactive power, and the magnitude of the complex power would be the apparent power. So that would be a way to solving this very simple exercise. Now we turn our attention to the dot convention. We have been using this model for the ideal transformer, and that is fine. In it we can define the voltage of the primary with that polarity, the voltage in the secondary with this polarity, the directions for the current in the primary entering like so, and the secondary leaving like so. But very often we prefer to use another symbol. This one for the ideal transformer. In it again, you say, well, how do I know which one of the sides of the primary corresponds to this drawing and which one to this one? For that, we use the dot convention. Check this out. We mark with the dot the top of the primary here, and we mark with the dot the top of the primary here. We mark with the dot the top of the secondary on this side, and we also mark with the dot the top of the secondary on this side. So we know. And now, no matter how we draw that circuit, we know which one corresponds to which one. And we say the voltage of the primary has positive on the dot of the primary and has a value of V1, and the voltage of the secondary has positive on the dot of the secondary and has a value of V2, which of course is V1 over A. And the current is entering the dot in the primary, like so, and is leaving the dot in the secondary. Please remember that. Current enters the dot in the primary, current leaves the dot in the secondary. You say, why are you doing that? I don't see the point of having those dots. Well, maybe not like that, but when those two windings are connected in a circuit, separate from one another like this one, let's say this is the primary of a transformer, this is the secondary of a transformer, at A for that transformer was given to us by the problem as being 2. So V1 is 2 in V2, but I2 is 2I1. How do we solve that circuit? Well, for that, we know the dot of the primary is 1, and the dot of the secondary is 1. So immediately we realize, hey, the voltage in the primary, given the way we chose the reference, node 1 and node 2, the voltage in the primary with that polarity is no other than the voltage of node 1, V1. Fine, but given that that is an ideal transformer with a ratio 2:2, if this voltage in the primary is V1, the voltage in the secondary will have the polarity minus at the top, plus at the bottom where the dot is, and that value is V1 over A, V1 over 2. And what else? The current. The current in the primary enters the dot like so. The value is unknown. I have called it IP. But the current in the secondary is leaving the dot and has a value that is 2 times IP, AIP. And then what? And then I've chosen already the directions for currents in the resistive branches here, there, and there. Not here. The current in this branch is given by the transformer's windings directions for currents here and there. Fine. What else? We can write a KCL equation for node 1. 2 currents going in. Yeah. This one on the top, V2 minus V1 over 3. Fine. This one on the bottom, exactly the same, V2 minus V1 over 3. And that is equal to currents leaving the node, 2 of them. And this one, V1 over 2. Plus IP, the current in the primary of the transformer. Now KCL2. KCL2, currents leaving the node, 3 of them, 1, 2, 3. No currents entering the node. Leaving the node, the one on the top, V2 minus V1 over 3. Another one that has exactly the same value. And on the bottom, 2 times IP. 2 equations, but 3 unknowns, V1, V2, and IP. We need a third equation. Where can we find it? Well, look at the branch at the bottom. That branch is pretty much an RV branch. You say RV, what about this? This is pretty much a voltage source with a value V1 over 2 and that polarity. So when you think of it that way, this current 2IP happens to be an RV branch current. That is voltage of the origin to minus 0 minus 100 plus the value of this helping source V1 over 2 divided by 4 plus 5. We have now three equations, three unknowns, V1, V2, and IP. We can solve for them, and with those values, we can find any current and any power in the circuit. Now, let's go for a full numerical exercise from the beginning to the end. Tutorial time. We're given a circuit with a two-winding transformer. You see the primary on the left and the secondary on the right. How do I know that? Because I was told that in the written problem. The transformation ratio for that transformer is A equal 3. Fine. All the values of the resistors are in ohms, and this is a sinusoidal source with an RMS value of 100 volts and 0 degrees of phase. Let's solve that circuit. Well, let's see how I proceed. Let me pick up a red color, and I'm going to choose this as my reference. Node 1 is going to be all of that is node 1, and there's going to be node 2. Nothing new, nothing new. However, choosing my nodes like that, immediately we say the voltage applied to the primary on the left side is just a V1, right? So this voltage here, so let me draw it here. This voltage is V1, the voltage in the primary. Well, but immediately if I say that, I know that the voltage in the secondary will have this polarity. What else? We know that the voltage in the secondary is going to be 1/3 of the voltage in the primary, and I write that V1 divided by 3. That is that voltage. That is interesting. So what we have found is that whatever value we have for V1 of the first node, V1 minus V2 is going to be V1 over 3. Let me write that equation, all right? I'm going to call that a transformer 1 equation. Yeah, I'm going to need only one in this case. And I say the difference between V1 and V2 in this voltage is just the value in the secondary, which is V1 over 3. We have one equation so far. Cool. And then what? Let me write KCL equations for nodes 1 and 2. For that, I will have to choose the directions for the branch currents in resistors. Fine. Let me say this is the current flowing through this 2-3 ohm branch. And this is the direction for this current. This is the direction for the current. The currents in the windings of the transformers are already preset. We cannot touch it. Remember, in the primary, current enters the dot. So let me draw it here like so. The current in the primary. What is the value? I have no idea. Let me give it a new symbol. I'm going to call that I primary, IP. But if that is the current in the primary, the current in the secondary is leaving the dot, so it has to be flowing like this, leaving the dot, and the value has to be 3 times IP, 8 times IP, right? So 3 times the primary current. Now we're ready to write the KCL equations in the transformer. KCL for node 1, for this one. Well, what currents we have there? Observe this, all of that. All of this is our node 1, agree? So the current going in are 2. The currents going in are 3 times IP, and at the bottom V2 minus V2 minus V1 divided by 4. And that is equal to the currents leaving the node, which are V1 over 5, V1 over 5, and at the bottom IP. Those are currents leaving node 1. Now let's write KCL to the Kirchhoff's current law equation for the second node. Current going in, only one at the bottom. 100 minus V2 divided by 5. Let me write it. 100 minus V2 divided by 5. And that is equal to the current leaving through the secondary of the transformer, 3 times IP. I don't have a clue who's IP. Plus the current at the top, that is V2, minus V1 divided by 4. Let's see, how many equations we have? 3. How many unknowns? V1, V2, and IP. We can solve that system of equations, yeah, for V1, V2, and IP. Let me do that very quickly, and then we go on with this set of slides. So we enter the equations into the equation writer of the HB50G, activate the equation writer. Write the first equation, which is V1 minus V2 equals to V1 over 3. Enter. We go back to the equation writer and we write the second equation. 3 times IP plus V2 minus 1 divided by 4 equals to V1 divided by 5 plus IP. Enter. Let's go for the third equation. Back to the equation writer. 100 minus V2 divided by 5 equals to 3 times IP plus V2 minus V1 divided by 4. And then enter, and we have the three equations. Now we make the three equations into an array. We have that array that represents a system of linear equations for the HP50G. What unknowns we want to solve for? V1, enter, V2, enter, IP, enter. 3, make me an array. We have the vector of unknowns we want to solve for. But before solving for that, let me go and check mode CIS and make sure that all my flags are cleared. So all the radio buttons are off. Done. Enter, enter, and we are ready. Symbolic solver, linear solution. And those are the voltages V1, V2, and the value of the current IP in the primary. From those, we could compute anything, any branch current, any power, anything. Now what happens when the transformer has more than 2 windings? Some transformers has a third winding, a tertiary, somehow 4, 5, 10, 11. Let's say we have a transformer like this one with 3 windings, the primary, the secondary, the tertiary, V1, V2, and V3. And we have 2 transformation ratios. There is a ratio from primary to secondary, A2, and another transformation ratio between the primary and the tertiary, A3, A2 to 1, A3 to 1. V2 is going to be the V1 voltage, the primary voltage, divided by A2. The primary voltage turns out to be the reference for everything. So, because A2 is a real number greater than 1, most times, V2 and V1 are in phase. Well, the relationship of V3 and V1 is pretty much the same with A3. V3 is V1 divided by A3. A3 is a real number, V3 and V1 are in phase. In short, all the voltages of all the windings in a multi-winding single-phase transformer are in phase. The same cannot be said about the currents. Look, the primary current, the secondary current, the tertiary current. The primary is going to be a linear combination of the currents in the secondary and tertiary, like so. The primary current is the secondary current divided by A2 plus the tertiary current divided by A3. And look at this, V2 and V3 are in phase. But when we connect different impedances to the port 2 and to the port 3, then I2 and I3 are not going to be in phase in general. They are not. And when we combine them like that, I1 is going to have yet another different phase. So in general, the currents in the multi-winding transformer are not in phase. Let's summarize. V1, V2, and V3 are in phase, but in general, I1, I2, and I3 are not. Let's use the dot symbols, all right? We have the classic symbol for a 3-winding transformer, primary, secondary, and tertiary, with the dots. And we have the new symbol, the one that we use very often, primary, secondary, and tertiary with the dots. In them, we defined that when this is the voltage of the primary without polarity, according to the dot, then the voltage in the secondary is this one, according to the dot is this one, V2, and the value is going to be V1 divided by A2, and the voltage in the tertiary is going to have this polarity according to the dot here and there, V2, and the value is going to be V1 divided by A3. Absolutely. And the currents are going to be entering the primary. The current in the primary is always entering the dot. And the currents in all the other windings are always leaving the dot, like so. I2 and I3. entering the dot in the primary, we always remember that, and the currents in the secondary and in the tertiary, they are leaving the dot. And the primary is going to be a linear combination of the secondary current and the tertiary current. Well, we are ready to do an exercise with a 3-winding transformer, are we not? Consider this scenario. We have a 3-winding transformer in a circuit. Primary, the secondary is on the far side on the right, and the tertiary. The dots indicate the relative polarities. Let's work on that exercise here. We know the values of the voltage source, 100 volts without polarity, and the resistors are given in ohms everywhere, and we have chosen the reference node here, the node 1 and node 2. And I've already chosen the branch current directions in each one of the resistive branches. What else? Well, we realize immediately that because of the choice of nodes, the voltage in the primary happens to be the voltage of node 1, so that is V1 without polarity. But if that is the voltage in the primary, given the dots and given the ratios A2 and A3, by the way, A2 is 2 and A3 is 3 in this exercise, then the voltage in the secondary on the far right is going to have that polarity given the dots, like that. And the value is going to be V1 divided by 2. A2 is 2. And the voltage in the tertiary is going to have this polarity and this value, V1 over 3. So you see, instead of having 3 separate unknowns, V1, V2, and V3, we have only 1. What else? We also know there is a relationship between currents in primary, secondary, and tertiary. The current in the primary enters the dot like so. We don't know its value. I'd call that IP. However, that is one unknown. What about the currents in the secondary? Leaving the dot like that, I2. And the current in the tertiary, leaving the dot, I3, like that. We don't know I3, I2, and IP. And because the combination of them is what we know, we cannot actually relate them one on one. We need to combine the 3 of them, and we will do that at the very end. Now we are ready to start writing equations, are we not? We write a K-scale equation for node 1. Currents entering the node, only 1 I3 down here, and currents leaving the node, I1, is going to be V1 over 4 at the top, plus IP at the bottom, plus I2 on the top, on the right, I2. Fine. That is KCL for node 1. KCL for node 2. Well, there is only one current leaving node 2, which is I3, and 2 currents going in. The one on the bottom, which is an RB branch, and the one on the top, that is I2. There. Currents entering the node is going to be V1. It's going to be 100 minus V2 divided by 5 plus the one from the top, which is I2, that is equal to I3, leaving the node. We have 2 KCL equations. However, we have V1, V2, IP, I2, I3. We have 5 unknowns. We need 3 more equations. Let's see what other equation we have. Right off the top, we say, hey, there is an equation here. This winding is telling me that V1 minus V2 is V1 over 3. Sure, let me write it down. Fine. Okay, what else can I write? What other equation can I write? I need 2 others. Well, I have this one. I have that this current I2 is the current in an RV branch. You say, what RV? Yes, the secondary of a transformer works pretty much as a V source with that value, V1 over 2, and that polarity. So this current I2 is the current in an RV branch. Voltage of the origin V1 minus voltage of the destination V2 plus the value that is helping of that V source V1 over 2 divided by the resistance 4. That is one equation. And last but not least, the one we mentioned before, the linear combination of the primary to the secondary and tertiary current. IP is going to be I2 divided by 2, which is A2, plus I3 divided by A3, which is 3. And we have now 5 equations with 5 unknowns, V1, V2, IP, I2, and I3. Solve them, we find all the values necessary to find every power in that circuit. And with that, we solve that one. However, a sort of summary and emphasizing that you should remember that on the primary, always current is entering the dot, and that in all the other windings, the current is leaving the dot. More, the relative polarity of voltages in all windings are given by the dots. And last, the current in the primary is the linear combination of the currents in all the other windings in the circuit according to that equation. For you to work on, I'll leave this little exercise. The primary is this winding on the left and the secondary is the one on the right. A is 5. Solve that circuit and report what is the RMS value of the voltage of node 1 with respect to that reference. Neo said to Morpheus, I know Kung Fu. And you know what Morpheus responded, right? Show me. Okay, you know ideal transformers? Show me. In a 3-winding ideal transformer with ratios A2 and A3, demonstrate that the input complex power to the primary is the same as the sum of the output complex power of the secondary plus the output complex power of the tertiary. Do that and you will prove to me that you really know Kung Fu. Thank you very much, and I wish you the best of lucks in your exams, both the midterm and the final exam.